Hello, and welcome to our Introduction to Series. In this video, we will introduce the idea of series and examine a few of their important properties. Recall, a sequence is an ordered infinite list of numbers. A series is obtained by adding together the terms of a sequence, so a series is an infinite sum of numbers. We generally use this sigma sum notation for series, where the lower number tells us where to begin adding and the upper number where to end. It is extremely important to be able to tell the difference between sequences and series. Let's look at a simple example, the sequence where every term is equal to 1. This sequence clearly converges to 1, as it is always 1. Let's create a series by adding these terms together. It should not be surprising that this series diverges to infinity, as we are adding 1 an infinite number of times. Since we cannot actually add an infinite number of things together, we must define a sum of a series using what are called partial sums. The nth partial sum of a series is obtained by adding the first n terms of the series together. Using this idea, we define the sum of a series as the limit of its partial sums as n goes to infinity. Let's try an example. Here we have the series with the kth term equal to 2 divided by the quantity k squared plus 2k. Here are the first few terms of the series, which we can use to calculate the first few partial sums. The first partial sum is always just the first term of the series. The second partial sum is the first and second term added together. The third partial sum is the first three added together, and so on. We want to take the limit of these partial sums, and this will tell us the behavior of our series. Rewriting the terms of our series using partial fractions, we see that the kth term is equal to 1 over k minus 1 over k plus 2. Using this information, we can come up with a formula for s sub n, the nth partial sum. Notice that most of these terms cancel out. So we are left with s sub n equals 1 plus 1/2 minus 1 over n minus 1 over n plus 2. Taking the limit of this expression as n goes to infinity gives us 3/2, which means that our series converges to 3/2. This idea of canceling many terms of a partial sum is known as telescoping. Let's consider an important family of series, geometric series. A geometric series is obtained by summing the terms of a geometric sequence. Again, we must consider the nth partial sum, which we get by adding the first n terms together, and then we'll take the limit of this expression as n goes to infinity. Using elementary algebra, we can see that if r is not equal to 1, then the nth partial sum of a geometric series is a times 1 minus r to the n minus 1 all over 1 minus r. If we take the limit of this partial sum as n goes to infinity, we see that this limit exists and is equal to a over 1 minus r if r is strictly between -1 and +1, and diverges otherwise. Geometric series are one of the few types of series that we will actually be able to determine the precise value of. It's vital to remember that the convergence or divergence of a series is determined by its partial sums. Noticing that the nth partial sum is the n minus first partial sum plus the nth term of the series gives us our first major result on series. Taking the limit of both sides of this equation, we see that if a sub n does not go to 0, then the series must diverge. This is known as the test for divergence, or the divergence test. As its name implies, it can only show that a given series diverges. It never can be used to show that a series converges. Let's try using it in a few examples. Here we have the series whose terms are cosine of 1 over n. It's always a good idea to try to apply the test for divergence when encountering an unfamiliar series, as it is the easiest of all series tests that we will have. Since the limit of cosine of 1 over n is 1 as n goes to infinity, the divergence test immediately says that this series must diverge. Let's now consider the series whose terms are natural log of n plus 1 over n. These terms go to zero as n goes to infinity, so the divergence test does not give us any information. However, if we use properties of logarithms and our telescoping idea from example 1, we can see that the nth partial sum of this series is equal to the natural log of n plus 1. Taking the limit of this expression, we see that the partial sums diverge to infinity. Since the sum of a series is defined as the limit of its partial sums, we see that this series diverges even though its terms go to zero. Here are a few more practice problems for you to try at home. The answers to these problems will be posted online. Let's stop here for now. In this video, we saw the definition of a series as the limit of its partial sums, how to sum telescoping series using partial sums, how to work with geometric series, and how to use the divergence test. Remember, the divergence test can only be used to show that a series diverges, and it does not say anything if the terms of the series go to zero.